Let's coming back. So um, let's start the third session. Oh, sorry. Our so we are very pleased to have our speaker, Laurence Perreault-Levasseur. Okay. Um, so she is currently a professor from University of Montreal and also in the Quebec AI Institute. And she's an expert in using AI and diffusion model, generative models, and also SPIs. And she will be talking us about all of the cool AI applications and also the theory behind it in our summer school today and tomorrow. So um, let's welcome her.
All right, I think I figured this out. Can you guys hear me? Yes? Okay, perfect. All right, so I'm gonna leave some time for people to walk in and sit down. So today I've prepared, I had some very intense lectures that were like a bit too extreme, so I think I kind of scaled it back, and today we're gonna take it a bit easier. For people who already know about machine learning, I've prepared you some other stuff you can look at while I talk about the introduction things. So, all right, so let's get started. Um, okay, so I'm going to start this by sort of making the classical argument for machine learning, saying that like today we live in this very special age in astrophysics and cosmology where we have a bunch of new observatories and telescopes that are coming online. And they are producing and are going to produce an unprecedented amount of data. And so because of that, kind of our traditional analysis methods, they're just not going to cope. And so if we want to be able to tackle those volumes of data and extract all of the information that's going to be in there, we're going to need some faster methods to be able to do that and some better methods. So that's kind of like the classical argument that people make when they want to justify why we need machine learning. But there's actually another reason why we need machine learning. And the reason is that this data is not only getting bigger in terms of volume, but it's also getting more complex in terms of the amount of information that it has. And so because of that, the sort of traditional analysis methods that we have that are very based on simplistic analytical models are just not going to be sufficient to capture the complexity of that data. So I think there's no better way to illustrate this than with those sets of images that I've stolen from François Lanus, who also stole them from Peter Melchior. So it goes like this. So here's a galaxy as seen by SDSS, which is a previous generation sky survey. And we think data is pretty simple. Like there's just one galaxy with a pretty simple shape. Sky is very simple. Here's the same galaxy as seen by the next generation survey, like the current generation survey, DES. And we see that already data is a lot more complex. There's a lot more stuff in the sky. And if we look at the same galaxy again as seen by HSC, which is a precursor for LSST, then clearly we see that there's a lot of stuff going on now. And so this is sort of a metaphor for what happens every time that we turn on a new instrument. There's like a whole slew of more information that happens in the data, and data gets a lot more complex. And so just to give a concrete example here, like there's a lot of blending between the different galaxies in this image. And so if I want to extract information about this galaxy, for example, like its luminosity, then it's going to be like very complex because I need to figure out how to deal with the galaxies whose light is getting blended with the main galaxy that I care about. So the reason why this is hard is because like traditionally, we've been fitting very simplistic parametric models to this data. And those are basically sufficient. Those are sufficient where our data is simple, but they're not sufficient when our data is getting more complex. And the thing is, we need those models to basically do like everything we want to do with data, right? Like we need data, we need models to do simulations, we need models to do inference, we need models to do model comparison, obviously, and like a lot of other applications. And like we even need models to do anomaly detection because in order to be able to define what an anomaly is, we need to have a model to decide what's anomalous versus what's not anomalous. So we need models, and it's becoming more and more challenging to come up with models that are complex enough to capture the complexity of the data. Like when we have simple data that's very low resolution and low signal to noise, like a simple parametric model is sufficient. Like for example, here, there's a strong gravitational lens, and if I want to parameterize the mass distribution in the lens galaxy, that's the orange galaxy, I can use like an elliptical blob with the position, a mass, an ellipticity, an angle, just about 5 parameters, and that's sufficient. But when the data gets more complex, like this strong lens at the bottom, that's just not going to cut it like at all. So I don't know what parameterization to choose to capture all the information that's in my model. And the thing is that this really matters because if we choose parameterizations that are too simple for the complexity of the data we have, we're going to have biased answers, and we're not going to know that we're biased. So this is an example where if we choose a noise model to analyze this mock observation, that's too simple, like we just assume that it's Gaussian noise, then we're going to get a completely biased answer as opposed to if we use the correct noise model, that is a lot more complex. So it really matters to get models that are appropriate for the data we want to analyze. All right, so this is where we come to machine learning. So machine learning, there's sort of 2 main motivations for it. The first one is speeding up analysis of data. And then the second is defining more complex models in a data-driven way. That's going to allow us to capture all the information that's in that data. So this is a kind of outdated graph of all the kind of things you can do with machine learning. It's kind of a very complex thing. We can do a lot of stuff with it. So most of the things I'm going to be talking about are going to be mostly supervised learning and somewhat like generative modeling, which is kind of unsupervised learning, but also supervised learning. So it's kind of in between the two. So it's going to fall mostly like, do you see my mouse? I don't know what you guys see. No, we don't see my mouse. OK, all right. Do we have a pointer? Nope. Oh, doesn't matter. OK, so here's my game plan for these sets of lectures. So I'm going to be talking about just an intro to neural network today as the first lecture, and I have no idea how long this is going to take. Might take very short, might take very long. I have a number of slides where kind of try to go through them. I'm going to talk about different methods for doing uncertainty. Oh.
You can just connect it.
I connect this,
Yeah.
and then what do I do? I wave my hands.
No, I think the point
Magic.
is somewhere. Huh.
Okay. That's okay, doesn't matter. It's not really that important. Okay. All right, and then I'm going to talk about SBI, and I'm going to talk about so there's a lot of ways. SBI is simulation-based inference, but now people call it like implicit likelihood inference or likelihood-free inference. And then I'm going to talk about explicit likelihood inference and diffusion models. So for people who already know about machine learning, you probably are going to get bored today, so I prepared something for you. So you can go have a look at the first 2 notebooks. You don't have anything to do. You can just like go through them and enjoy. They're kind of funny. One of them is about a deep dive in linear regression, and the other one is about Bayes' theorem. And the third one is one about SBI that I'm going to get a lot more into today/tomorrow. And it's like you have to fill in the blanks to build the model. So you have more work to do. So I think you can get yourselves entertained. Or you can just leave if you want. But yeah, so if you already know what an MLP is and what a CNN is, this first lecture is not for you. So you can have fun here. Unless you don't want me to talk about what an MLP is. If you guys all know what an MLP is, I can just skip this and go into the fun stuff. No, you want to know what an MLP is? Yes, OK, perfect. Sounds good. OK, so let's get started. Introduction to neural networks. So we're going to talk about linear models, and then we're going to use that to build fully connected neural networks, also called MLP. And then we're going to build convolutional neural networks, and then I'm going to give a bunch of tricks of random stuff at the end. So that's our game plan for right now. OK, so the simplest possible like parametric model that we can come up with is like arguably a linear model. And you might say, OK, a linear model, like I've been doing that since my first year undergrad in my lab class, like that's what we were doing. But the reason why it's important to really understand how to build a linear model is that that's the fundamental building block for a neural network. Like a neural network is basically just stacking linear models on top of each other. So the way we build like neural networks is by stacking linear models, just like we build Legos. Okay, so let's get started. So linear models is basically the art of fitting a line through data. So let's say that I have a bunch of data points here, and these are noisy data points. And what I want to do is figure out what are the parameters for a line that goes through that data. So because x and y are one-dimensional in this case, I'm looking for two numbers, a slope and a y-intercept, right? And basically, these are, I can frame that as like, this is the relationship I'm looking for. So I'm looking for the things that go in the A matrix that's there. So A and X are related by a matrix operation. Y is a vector of like noisy data. In this case, it's not a vector, just one number. X are the parameters, typically, in an inverse problem. A is like a linear model in this case, so that's a matrix. And so usually, like when you talk about inverse problems, that's going to be like the forward models. That's going to be like the physics, like all the physical models going to go in there. So it's going to be the physics. And then n is a vector that has noise. So in this case, it's just one-dimensional problem. So it's just a number that's noise. So and then if I plot here what the true data generating process here is, so like if I knew what the A matrix was, I could plot this straight line. That's like the ground truth that I don't know what it is. So that's what I'm trying to get, right? So, okay, so if the noise is Gaussian distributed, so what that means is that the likelihood for my data is going to be given by a Gaussian. So the easiest way to infer the posterior for the possible values of like the parameters that I'm looking for is to use Bayes' theorem. And in that case, so Bayes' theorem can be written like this, where like this is the posterior. You guys I saw a bunch of discussion on Slack about Bayes' theorem. So I'm assuming that you know what Bayes' theorem is. Who knows what Bayes' theorem is? Everybody knows what, no, not everybody, okay. So Bayes' theorem is basically, so what we want to know basically when we, like, so x is our parameters that we're interested in, and y is a vector of data, right? That's what I said in this like inverse problem here. So y is the data and x is the parameters that we care about. And so what we want to know is what's the probability of the parameters we care about, the x given that we saw some data, y. So that's the posterior, that's what we care about. And Bayes' theorem allows us to, so that's really hard to compute usually. So Bayes' theorem is basically just doing some math identities in order to write this probability distribution down in a way that we can calculate it. So we can write it down as the likelihood, which is the probability of observing some data, assuming that the true parameters were some set parameters. And that's the noise model. So that's where the Gaussian distribution is going to be. Times the prior and then divided by the evidence. So the evidence is like usually not as important unless we want to do model comparison because it doesn't involve x. So if I just want to compare different possible values of x, that's just a common denominator for everybody. So I don't need to care about this usually. So if my noise model is Gaussian, basically finding this posterior distribution is going to boil down to finding the parameters that minimize this chi-squared because that's the exponent of my Gaussian. And that's what you've done in your undergrad. And so I can define a bunch of like matrices. So I just wanted to write this down for completeness. But basically, I can solve for what the weights for the slope and the y-intercept are, the entries in the W matrix. And I can compare that to the ground truths because these are all simulated data points. And it works. Math works. That's good. So for a linear model, we can solve this exactly if we know that the noise distribution is Gaussian, which is not always the case. Okay, so that's for regression, but sometimes that's not what we want to do. So sometimes what we want to do is to classify between different sets of points. So let's say I take exactly the same data points, but now we clearly see that there's like two clusters in my data points, right? There's like one that's kind of like on the right and that's one that's on the left. So this could be like red points and blue points. And what I want to know is like for new points, I want to automatically know which cluster they fall into, if they're red or if they're blue. And so in that case, what I want to know is find a line, but that's going to be a boundary between the two clusters instead of a line that fits through the cluster. So I want to find the equation for a line that separates my two clusters, and that's classification, basically linear classification. So that's also doable. Oops. So that's also something that we can do in the case where like this is 2D. But in the case where this is really high dimensional, like let's say that in a place where I want to classify cats from dogs, and I want to fit a line between one of those clusters that's images of cats and one of those clusters that's images of dogs, that's going to be really high dimensional, right? Because instead of being just like 2D like this, every pixel in my image is an independent parameter. And so that means that if I have like 100 by 100 image pixels, I'm in 10,000 parameter space. So I need to fit this hyperplane in this 10,000 dimensional space. That's going to be kind of difficult. So basically what we're going to do is we're going to phrase this problem of finding like fitting a line through data and finding a boundary between two different clusters in some unified framework. And that's what we're going to use as the building block for building neural networks. Okay, so I'm just going to go through that. So the way that we're going to do that is we're going to go about solving this problem in 2 steps. So first, we're going to have some examples where we know what the answer is. So we're going to have either some like x points for which we know what the y value is. So that these are going to be our training examples. We're going to basically use that to learn what the slope is. And then when we have new points, we're going to use those learned like slopes to predict what the y value is. Similarly, when we have the 2 clusters, we're going to use those like points where we know which clusters they belong to decide where the boundary is. And then once we've learned what the boundary is, we're going to apply it to new data to decide which cluster they belong to. So that's like kind of a 2-stage process. In supervised learning, there's always this 2-step process. First, there's the learning, where we train the model, and we learn what the function is that we want to learn that allows us to do the task we want to do, and then we apply it to new data where we don't know what the answer is. Okay, but it's supervised, so there's a bunch of data for which we know what the answer is. That's kind of like the paradigm framework. Okay, all right. So we're going to have this parametric model, and we're going to try to learn the parameters of that model. So in general, this could be like, so this could be some function f, any function. That function is going to take in like the pixel values of my image. And then there's going to be some sets of parameters that I don't know what they are yet. They're going to mix together in that function in some way. And then out's going to come some output that's going to be in the space that I care about. So it could be like a prediction, for example, the value of the mass of the galaxy or the redshift or something. It could be like some vector of outputs, or it could be a class that tells me which class this galaxy belongs to. So in a classification problem, I could want to classify like which morphology of a galaxy this is. In a regression task, I could try to learn like values of properties for what that galaxy is. Okay, and then that function f, as we said, the first step is that function f is going to be a linear model. So actually, those parameters w, they're just going to be a matrix. So they're going to be the entries of a matrix that are going to multiply the pixels of my entry, and then they're going to map that into my output. Okay, so I know this sounds like a bit abstract, but like I'm going to give a concrete example, and there's also going to be a bias because linear models have a y-intercept. Okay, so I'm going to give an example that's a bit more concrete with like examples of things that we see on the Earth because it's more intuitive. So CFAR10 is this data set that's like pretty small. It's 32 by 32 by 3 color channel. So it's like 3,000 something pixels per image. So it's something that you can play with and with your computer. So it's like a good data set. You can go download it online and you can try to train machine learning models with it. So it has 10 different classes that are named here. And so, and they also have like for every image, you know which class it belongs to, basically. So if I want to write a model that's going to classify for a given image, it's going to tell me which class it belongs to. So I could have this like function that takes those parameters that tell me that I want to learn, and it's also going to input like the values of the pixels for that image, and it's going to output 10 numbers that tell me which class it belongs to. So typically when we want to do classification, there's going to be like, in that vector of outputs, we're going to have a 1 for the value of the class that we have and zeros for the other class. That's called the hot one vector. So like if this is a car, I think it's a car, so the class car is going to have a 1, and all the other like 9 classes are going to have a zeros for the label for that class. Okay. So we know that we want to have a matrix multiplication in our case. So like, I'm not going to write a 3,000 pixel long vector. So I'm just going to assume that there's 4 pixels in my image. Oh, I don't have the pointer would be very nice right now. Okay, so I have you guys really, oh, you see it? Yes, victory. Okay. So I'm assuming that my image, my input image has 4 pixels. Okay, so this is my input image. So what I'm going to do is I'm going to unroll it in a vector. So I just unroll it and I put it here. So this is my input. Okay, they're the same number, they're just in a vector now. And I have this matrix here that have the weights that I don't know. These are the parameters I'm trying to learn. So I want this matrix to map my pixels to the class that I want. So let's say that there's 3 classes. There's like cat, dogs, and car. So I would like this matrix to map from the space of pixels to the space of classes. So it's going to have 1 column per pixel because it needs to map like the number of pixels. So if there's 4 pixels, there needs to be 4 columns. And there's going to be 3 rows because there's 3 classes. So there's 1 row per class and 1 column per pixel. So if it was a 3,000 something like vector for the pixels, then it would be 3,000 something like columns in that matrix. And if there were 10 classes, there would be 10 different columns. So because this like matrix here has like, if you look at just the pixels that correspond to like the first class, like the ones that are in red here, they have the same number as the number of pixels I have, right? So I could think of like rolling those back into an image, and they would be like kind of a template for what my weights are looking for in the image to match to that class, okay? So basically, if I want to know, if I ask the questions like, what's the right value of the, because I didn't tell you like what's the right value of W. Okay, so there's a magic process that I need to do to figure out what are the right values of W to get the answer that I want. And once I've done that, then that W matrix is fixed. It doesn't change anymore. So I gave it a new like image, and it's going to tell me which class it belongs to if I do the multiplication. Okay, and I can look at what are those different rows that correspond to different classes. So for CFAR10, the different templates are this here. Okay, so it looks like garbage, but it's like really interesting to look at what it looks like. So you can see that like the template for car, once I roll it back up in an image, it looks like a red car because a lot of cars are red. So basically the templates are like the average of all the training data. That's what it's learned. And you can see that the horse here is kind of on grass because a lot of horses tend to be on grass. So they're always going to be like green grass at the bottom. But then the horse kind of has 2 heads because in all the training set, the horse can either be say, facing left or facing right. And the template is looking for like the average of the 2. So it's looking like no horses, but it's kind of like the average horse looks like a horse with 2 heads. Yes?
Thank you. So I'm very new to all this stuff, so maybe a naive question, but when you actually do the training data to determine the W matrix, the values in there, surely it's not as simple as if you know the image you're giving it as a car, zeros everywhere else, and this 1 in the row that's supposed to be a car.
So ideally, that's the output you want, right? To be sure, like that's what the label says. Now you're not going to get there, but I haven't told you how to find the W.
Okay.
I didn't tell you the secret. I just told you like once you're done, like there's a process that I'm going to tell you how to do, and then once you're done, that's what you end up with.
Gotcha. Okay.
Okay.
Thanks.
And it's not going to be perfect, obviously, because
Right.
no horse. Like you need to have a perfect match for it to be 1 and 0 everywhere else, and there's no horse with 2 heads.
Okay. Yeah.
Okay. But like it's kind of interesting to see that this is what, and that's the thing that's cool with like linear models is that they're very interpretable. It's very easy to look inside them and to see what they're doing. Like clearly that's what the model is looking for. It's looking for the average of the training data. And so I can kind of see like the average horse, the average car, the average truck. Like the truck is kind of clearly like on a road or something. And the ship is over blue because it's like over water because ships tend to be on the water. Okay. So
I had a question, sorry.
yes.
Right here.
Hi.
So what you're tracking or the data that you're putting in is basically the value of your color at certain pixel spot. Is that basically what the data is that you're inputting?
So what it's going to be doing, so basically like once I have those templates, I can put them in this matrix here and like those biases. And then if I have a new image, I'm going to just matrix multiply the 2. And I'm going to get a set of answers that are scores. And the scores that has the value that's like the largest is going to be the one that I'm going to say this is.
I kind of understand that. What I'm asking is about the input image. Like, what are you tracking in the input image? Are you just looking at
The
values
pixel value. So these are RGB images, so they're RGB pixels, right?
Okay, so you're looking at the RGB number basically at
yeah,
each.
exactly.
Okay.
Exactly. So these are like these are just RGB images. So typically they'd be like in a range of like I mean, we're astronomers, so we don't care that like it's like between 0 and like 256.
Of course, yeah.
But like typically those images are going to come in that size.
Okay.
But then you can use like a FITS file, and then it would be like whatever dynamic range you have in your image.
Okay, that makes sense. Thank you.
But it could be like anything. But like in this case, because these are images that have been taken with like a CCD camera that's meant for the Earth, it doesn't have like 8 bands. It has 3 color channels. And so it's like a 32 by 32 image, and there's RGB filters. So that's why it's like
Okay.
by 3.
Yeah, I got it.
Make
Okay,
sense?
thank you.
Okay, but you could do it with like 7 filters, right? Like it's like the whole framework is built that like all these things are completely flexible. So you can, whatever data format you have, like you can think of like an LSST image that has like all your bands that you want to have, and then that's what the data you're going to put here. Okay? All right, perfect. Okay, so we have those. Okay, so now, yeah, so we can kind of like see basically like what's like the problem with like linear filters is that sometimes like if I think of those images like in high dimensional spaces, like the horses that have the head one way and the horses that have the head like another way, they kind of form 2 subclusters. And then I'm trying to like fit a line to separate those, but you cannot use a line to separate things that have like multiple like blobs like that. So it kind of doesn't work. So we can kind of like think of like a linear classifier as trying to put like a hyperplane in like pixel space that try to separate the images from one class versus all the rest. But then if there's multiple classes, multiple like clusters of that class, then it's not gonna work, right? And so that's why it kind of like does not work perfectly. Okay, so now the question is, how do I find the right value of W and like the bias? Like, how do I find the values that I have to put in that W? So if I want to find those like W's that give me the best possible line, I have to do 2 things. I have to define a loss function. And so the loss function is how unhappy I am with the current values of the output of the network. Like the current values of the weights that give me an output, I have to tell the network, I'm not happy about this output like this much. So it quantifies by how much the network is wrong. And then I have to find a way of optimizing that loss. So finding the value of the weights that make that loss better. Make sense? Okay. So basically, the loss function tells me how bad the current line that I have is, because every specific value of W gives me like a line or a plane, and that like line is either good or bad, and it quantifies with a number how good or bad it is. So for classification, typically the loss function that we use, like this quantification of how good the line is called the cross entropy loss, or it's like softmax, it's called sometimes. And in that case, like the scores that come out of the neural network are interpreted as log probability. So I just say, okay, this number that came out is a log probability. So I'm going to exponentiate it to get a probability, and I'm going to divide it by the sum of all of the numbers like this, so that it's a normalized probability. So now for every output of the network, I have a probability for what's the probability of that class. So the class that has the highest probability is the one that I'm going to pick as the one that the network predicted comes out. And so the cross entropy loss is basically saying that I'm going to take the one that was the right one and get its log prob, and that's going to be the loss, because I know what the real answer is. Because this is supervised learning, so I know what the real vector of a hot one is. So I know which like class has probability 1 versus all the other ones are 0. And so the class that has probability 1, I get its probability, and that's the loss function. And so the network's going to try to make this as close to 1 as possible. So it's going to try to maximize the probability of the correct class, basically. So if the probability is not 1, not good, do better network. And then we want to average that over the whole training set. And then, so we have to like take the average over the loss of every possible example that we know the answer for. Does that make sense? Yeah? Okay. So that's for doing classification. Do you guys know, I cannot write. Do you know what the why I'm calling this cross entropy, by the way? You guys are all physicists, right? No, yes. You know about Shannon entropy? You know what entropy is? Like you've done like thermodynamics in your undergrad, right? And then at some point, like your teacher went, oh, by the way, like entropy is also Shannon entropy, and that's the information definition of entropy. That happened at some point, right? And then that never came up again, right? Okay, so that's what we're talking about here, okay? So it's basically entropy is the amount of, I really wish, okay. So entropy is basically it's a way to quantify the amount, the expected amount of information from taking a new measurement. Okay, so like the way that it was written, I had to write really big for you guys to see, right? If I write this big, do you guys see? Yeah? No? Yes, okay. So I take the sum over the states of the probability of the state times the log prob of the state, right? That was Shannon entropy. And so what this is like basically the expectation of the log probability under the probability of the state. So it's like this is an expectation value over all possible states, okay? So now I have like 10 classes. I have like a bunch of like training set, and so my expectation would be over all like my possible training set over all the classes. So this quantifies the amount of like information that I get on average if I make a measurement, okay? And so if I have now like a model that's training, it has probabilities that are not quite right. So instead of being the true probability here, I'm evaluating like not the right probability. It's like Q, so it's another function that I'm learning. I'm saying it's the probability, but it's not the real probability. But then the expectation is taken with the real probability of like the real class, what it is, because I know what the label is. So I'm taking the expectation with like the real probability, because that's like reality. I have real labels of the log prob with the wrong probability. So that's why it's called the cross entropy loss. And then the probability is either 1 or 0, the true probability. For the classes, it's 0 for the wrong classes, and it's 1 for the true class. So in the loss function, we just keep the prediction for the true class. And that's the one we're trying to maximize. So that's kind of the reason why this works. Okay, make sense? You guys here did not see at all what I was just doing, sorry. You guys saw? Okay, perfect. Okay, so that's why it's called cross entropy, because it's like, there's the real universe that works with P, and then your learned entropy is the log P that you're trying to quantify. And it's also related to the KL divergence, by the way, but we're gonna get to that tomorrow. Okay, so that's for cross entropy. But then sometimes we don't want to, so that's when we're trying to do classification. And we have a vector of log ones with like the class, that's one. But then when we're trying to do regression, that's not the log function that we use. When we try to do regression, we use mean squared error typically. And that's kind of working under the assumption that the error is Gaussian. And so mean squared error is like the chi-squared. This is all related. And so basically, the mean squared error is like this. So if we, in the case where there was no covariance between the outputs of the things we're trying to measure, and it was all equal for all the outputs, like the error was equal for everybody, and then we had like a Gaussian noise, then this boils down to like optimizing the chi-square function again. So this is the mean squared error loss. So for doing regression, that's like the default thing that everybody uses. But they never tell you that the underlying assumption is that you're assuming Gaussian error. But that's what's going on. Okay, that went way too fast, sorry. Okay, so for the whole training set, then we need to average over training examples. So that's one training example. So we average over all the training examples, and that gives us like overall the training set how unhappy I am with what my network is predicting. So now that we know with a number how unhappy we are, we can start finding the weights that make it better, right? Make sense? Okay, you have to stop me because I have no idea how long that took. This is gonna be so long. Okay, all right, so this is like where we are. So we have like an input here, and we unroll it, we make it a vector, we have those weights, and that bias, it gives us like a bunch of scores, and then we can compare those with like the true scores that we know through a loss function. And so the only thing we have to do now is optimizing to find the weights that give us a better loss function. So the next thing we need to do is optimization. So we're trying to basically find the values of weight. If this is like a representation of every dimension is one value of W, one element in that matrix, and we're trying to walk towards the place that makes the surface is the loss function, and we're trying to walk towards the place that's minimum. So you guys know how to do that. It's just gradient descent, right? So we just want to walk in the direction where the gradient of the loss is getting like as small as possible. So we want to walk in the direction of negative gradient. So this is just gradient descent. So that means that we are going to need to know what's the gradient of the loss with respect to the weights, because that's the thing we want to change to walk towards less loss. Because we need to know gradients. Like usually in our physics classes, we learn to take gradients with like finite differencing, because this is on a computer. But actually, finite differencing here would be very, very, very slow, because we typically have like millions of weights, and so that would be way too slow, and on top of it, it's going to be really noisy. Actually, all the functions that I've introduced, they're super simple functions, and so I can just write down the gradients analytically. So it's much better to write with like the real analytical gradients. And so in machine learning, that's always what we do. We always have the true gradient, and that's one of the reasons why it's so powerful to code with differentiable code, because we have, okay. So we can do, to calculate the gradient, we can do it over the whole like training set. So that's what we want to do. So then we walk towards like the place of minimum, the minimum place in the weight space. But then one of the things that happen is what's going on here. We can converge to like a saddle point, and in high dimension, there's a lot of saddle points, so we're never going to end up in the minima. And then another thing that's really important is the learning rate, because we can end up jumping around the minimum without ever converging to it. So whole batch gradient descent is actually not very good, because we're going to end up converging to local minima or to saddle points in really high dimensions. So what we actually end up doing is mini batch stochastic gradient descent, which is that instead of optimizing, like calculating the loss over the whole training set, we take a small amount of it, and then we calculate the gradient. And that gradient is going to be noisy. And then the next time that I calculate the next step of gradient descent, I'm going to take a different amount of, like a different set of training examples. And so every time I get my gradient, it's going to be a bit noisy. So that's going to avoid, so instead of like going straight down, I'm going to just be jumping around. And so it's going to end up preventing me from getting stuck on saddles. And it's also going to end up allowing me to jump outside of local minimum. So I'm going to end up converging at a much better place. So in theory, it doesn't converge to the real minimum, global minimum, but if we decay the learning rate, then it actually converges. So this is basically what we do. So the extreme version of this is to do pure stochastic gradient descent, to compute the gradient on a single training example before taking a step in the gradients, but that's just way too noisy. So this is our just like the example. So this is pure like whole batch gradient descent. This is like mini batch gradient descent, and the purple one is like stochastic gradient descent. So now you know how to train a linear classifier or a regressor. And all right, we're going to stop here for like 10 minutes, and then we're going to keep on going.
Next speaker. Let's have a 10-minute break. Plan to talk about deep learning neural nets in this session.
Yeah, well, we'll see how this goes. But yeah.
It's just, yeah, I just saw it. It's just behind your laptop.
Behind the laptop?
What's here?
Oh,
Yeah, I tried to find
Uh-huh.
because I checked it.
Well,
Does it work?
But the
Nope.
computer pointer is even better because people online can see this all.
Yeah. It's good that the computer pointer is working.
And what else was going to say? Yeah, you can take as much time as you want. Don't feel you have to rush. This is great.
Okay. But at some point, these kids are going to be tired. Like, they're going to want to go home. You guys are okay?
I have a question.
Yeah.
So you said how saddle points can be problematic and local minimum. What about, I heard that overtraining your data can also be a problem. So.
Oh, yeah. That's like at the very, yes.
So you talk about that later.
But I mean, it's like in my bag of tricks at the very end. So like, yeah. So typically what you do is you do like, when you have your whole training set, you never train on the whole thing. You split it in three. You get the biggest part of it, you use it for training. Then that's the training set. Then there's a second part that you use for, I'm gonna stop this because I'm screaming in the